Okay.
Okay, Assalamu alaikum, everyone. I'm going to be explaining how fats are absorbed in by our body. So we all know. We all know that the food that we eat, the nutrients from the food that we eat, are absorbed by the small intestine. So similarly, the fat in our food is also absorbed by the small intestine. And so I'm just going to give a zoomed out version of what actually happens with the fat once it reaches the small intestine. Um, the fat molecules are in so the small intestine has specialized epithelial cells that can absorb the nutrients from the food, which line the lumen of the small intestine, and the lumen is obviously the hole through which the food we eat travels. Uh, so this cell is our epithelial cell, and the small
Also mention what epithelial cells are. Cells
uh,
lining
the cells lining the um,
intestines.
intestinal wall, and so the lipase must function in an aqueous environment because most of our body functions in a water loving environment. But this is a problem for the lipase because fats are, as we know, non-polar, which means they're hydrophobic. That means, like, you can say they're scared of water, and so they're hydrophobic and they're insoluble, and so the lipase cannot digest them, cannot work on it. uh, and so basically, fat is triacylglyceride, which is this molecule. I'm going to come to it in a bit, but mm, uh, I also want to mention that bile, the bile which is secreted by our liver, and then stored in the gallbladder and then is secreted into the ileum of the small intestine. The bile acts a lot like the detergent that we use to wash our hands. And if you have ever experienced, whenever our hands get greasy, we use water to wash it off, because what actually happens is, like, if we zoom in and go to the molecular level, um, this is the fat globule, and, like, you can say the grease on our hands, and it does not it's non-polar and water is polar, and it does not simply come off by running water. So we use soap. Soap has two parts. One is hydrophobic, other is hydrophilic. uh One is polar, one is non-polar.
आवाज यार चेंज है टोटल आवाज
One is polar and the other is non-polar. So the polar part of the water is going to be facing the polar part of the soap is going to be facing the water, and the non-polar part of the soap is going to be facing the grease molecule, the fat globule. Um, and so it's these soap molecules are going to take small pieces of the fat away, and so it turn and make them into small micelles, which can be then washed off by the stream of water. And
this whole structure is called a micelle, and these are water soluble, right? So now they can be easily run off by water and soap.
and so our hands are free of grease. So that is this exact same thing that happens in bile. You can take these soap molecules as the bile molecules, and this is the fat. So the bile does the same thing. It turns the big fat globules into small micelles, which increases the surface area and then makes it easier for the lipase to act on the micelles. So these micelles are basically the triacylglyceride fat molecule, and it's made of glycerol and fatty acids. And the glycerol is like this backbone structure made of carbon and is attached to the carboxyl group via the oxygen. And we need, this is a too big molecule to diffuse into the intestinal cell, and so it needs to be broken by the lipase. So we have to hydrolyze it. The lipase hydrolyzes the triacylglyceride molecule, the fat molecule, and adds water. We know that water is made of hydrogen and hydroxide ions. So the hydrogen ion attaches to the glycerol part of the fat molecule, and the hydroxide ion attaches to the carboxyl part of the fat molecule. So these, and of course there are three of the fatty acids made, because there are three carboxyl groups and one glycerol. Now these molecules are small enough to diffuse into the cell, in the epithelial cell of the small intestine. And so they again they enter by diffusion the epithelial cells of the small intestine. Over there, they're turned back into triacylglycerides, fat molecules like they were before, because that is a compact unit in which we can send them off to various tissues where they are needed, like the adipose tissues where they can be stored for later use. Their energy conserves.
Okay.
Yeah, so then they are packaged and with
lipoproteins,
carrier molecules, lipoproteins, and they form this structure with the.
Why are they packaged? Also mentioned. Because proteins are water soluble, they are polar, and so it would be easier for the blood plasma to carry them.
Yeah.
And so, yeah, so now this structure here of chylomicron is the same as the micelle that you saw here. Okay, the same as the micelle here, with the hydrophobic core, that is the non-polar core surrounded by the polar heads. This structure is called chylomicron.
So this is the cholesterol. This also includes the cholesterol we ate, and also the fat from our food. And this whole molecule, this whole structure is, while it is small enough to pass through the cell membrane, it is not small enough to pass through the fenestrations or gaps in the capillary. So the small intestine has a rich supply of oxygen and nutrients, because obviously the function of the small intestine is to absorb nutrients from the food so that our body gets it. So we need a rich supply of blood, but the fat molecules, the chylomicron, cannot enter the capillary because the gaps or fenestrations are too small for it to enter the bloodstream. So that's why there are lacteals, which are lymphatic capillaries, and the chylomicron, they have bigger pores than the normal red blood.
The capillary walls.
The blood capillary walls, they are bigger than them, and so the chylomicron enters the lymphatic capillary, enters the lacteal, and the lacteals. Once it enters the lacteal, it's gonna reach our blood circulation, and that's how it's gonna reach the parts of the body that needs it.
Right.
So there are also lymphatic vessels all over the body. So some of them run up our legs and drain from our arms and then down our neck. And basically all of them combine in these ducts. The left thoracic duct and the right thoracic duct, more of it drains down the left thoracic duct, but some of it also drains down the right thoracic duct, where it then enters the subclavian veins. And the subclavian, once it reaches the subclavian veins, it's now in the bloodstream and can reach the rest of the body.
Right. Okay. Thank you very much on this. You did a good job. I think you mentioned all the points, but if there's any Yes, yes, she has almost mentioned all the points. She did not miss any point, but if you think it was too much for you and if you have any questions, please go ahead and ask. Basically, to cut it short, to give you a summary of what's happening in a, in like as few words as possible, let me do that for you. Basically, the fats are big, they are nonpolar, they do not dissolve in water, so their absorption is difficult. So what bile does is that it, breaks them down into smaller pieces so that their digestion is easier by these lipases. And after they are digested into smaller molecules, they diffuse into the intestinal epithelium, where they are packaged back into chylomicrons, into structures called chylomicrons. And these structures are big. They are too big for the pores in the capillary walls. So the lacteals instead take them because the pores in the lacteal walls are bigger. So that's how the fat is absorbed into the lymphatic system, to cut it short. If there is any question, please go ahead and ask. Jazakallahu khairan for the encouragement. And you guys can also volunteer, can also come up with small presentations like that. Choose a topic that students find difficult, like any topic for which you think, it's not quite clear in our minds. Go ahead, make a presentation, search on it, find out, make a diagram, make it a story in front of you, in your mind. Go ahead and explain your class fellows. Not any subject, the science subjects, physics, chemistry, biology, you are most welcome. But I want good, comprehensive, not just reading out, to make a story in your mind.
Yes, Yusra, bile is produced in liver.
Yes, bile is made in the liver, but it is stored in the gallbladder. And when we eat, the gallbladder is stimulated and it contracts, and the bile is secreted into the lumen. So it is released. Right? So is that clear now? Is it clear now?
Thank you, Hiba, Hala, Azwa, Laiba.
Jazakallah khairan for your encouragement. Yes, you guys can also come up and do the same, okay, for any topic that you find difficult. Okay, now let's move on to our chemistry questions, past paper questions. Okay. Okay, let me share my screen. Let's start with those questions that I posted in the group. Okay. Yes, these questions. Okay, redox reactions, okay? The reactivity series of metals given below contains both familiar and unfamiliar elements. For most of the unfamiliar elements which are marked starred, their common oxidation states are given, right? What is the oxidation state of barium? Now, the easiest way of finding out the oxidation state of barium is to look at its group number. What group number is it? And so it'll be easier for you. So barium is in the second group. I have the periodic table in front of me, and you guys should also have. So barium is in the second group, and so second group elements have +2 because they have only 2 electrons in their outermost shell, so they lose 2 electrons, right? So that's easy. Name an unfamiliar metal starred whose oxide cannot be reduced by carbon. Now, unfamiliar meaning the ones that they have starred, right? Whose oxide cannot be reduced by carbon. Now, for this, you have to have the reactivity series. I noticed that in these past papers, they have given only parts of questions. They have not given the whole question. And so then it is difficult when you only have a part of it. So for this, to be able to answer this question, you have to know the entire reactivity series. Maybe they gave it in a part of, and this is a part of a question, maybe they gave it in the question. But whatever, I searched the whole reactivity series, and on Wikipedia, I found that chromium and palladium, they are less reactive as compared to carbon. And so any metal which is less reactive than carbon, carbon cannot reduce them. Oh, sorry. Chromium and palladium, they're above carbon. And so carbon cannot reduce metals oxides of those metals which are more reactive, right? That's why the higher reactive, the more reactive metals, they are obtained by electrolysis, right? Because they cannot be reduced by carbon, right? So chromium and palladium are one of those. So we are left behind, and even barium. What am I saying? I'm getting confused here. But okay, only barium and lanthanum are the ones which are above carbon. I'm sorry, I got a little confused. Barium and lanthanum are the only ones that are above carbon, and therefore carbon cannot reduce their oxides. Okay, so, and barium is more familiar. So I think lanthanum is a better alternative. And so you can write lanthanum as your answer. Okay, chromium and palladium, chromium and palladium, I think, are less reactive than carbon, and therefore their oxides can be reduced by carbon. Okay, I think I got it right now. Okay, is there any question? Any confusion? Okay, what about aluminum? Aluminum is not given. Aluminum is not given. We have to choose from the table. Yes, we have to choose from the table. Will it be wrong if we write barium? No, I don't think so. I think barium is also acceptable because they starred it. They starred it. So they want you to write one of the starred metals. Okay, part 3. Why should you be able to predict that metals such as iron and chromium have more than one oxidation state? Because they're transition metals. Good job, good job. Yes. Yes, because they are transition metals, right? And transition metals have more than one oxidation state. Okay, everyone got that right. Okay, good. Now, ozone is an oxidant. It can oxidize an iodide to iodine. What would you see when ozone is bubbled through aqueous acidified potassium iodide? Yes, who will answer this question? What will you see if we bubble ozone through aqueous acidified potassium iodide? So we know iodide is what? What's an iodide molecule? Okay, okay, yes, yes, the color of solution will change from colorless to brown. Why? Why? Because? Yes. And I also wanted you to answer my question. What is iodide? What is acidified iodide? Iodine is colorless when iron. See, no. See, this is not the, you're not saying the keyword. You're not saying the keyword. Reducing agent. Thank you very much, Afan. Yes, yes, I was looking for this. Iodide is a reducing agent, right? So it will get oxidized itself. It will get oxidized itself because it is a reducing agent, right? And so, and why do we use, why are all of these reducing and oxidizing agent acidified? Did you ask this question? Did you ask yourself this question? Why are they acidified? You asked, Hala? No.
She asked herself.
Okay, then did you get the answer? Did you get the answer? No. Okay. I am sharing my video. The reason why we use these oxidizing and reducing agent in an acidified way basically is we want to ionize them. We don't want them to be in the molecular form. Even the water, because they are all aqueous, even the water should be in the ionic form. And And acidifying is a good way of ionizing them, because more the ions you add into water, those ions help in ionizing the rest of the water molecules. Now, this is the equation which is given in the question, right? This was the equation, right? Yes, that's the equation that was given in the question. Okay, so let's see what's happening to iodide. The oxidation state of iodide on the left-hand side is -1. Here it's 0, right? So the oxidation state has increased. It has increased, right? So oxidation state, when it increases, it's called oxidation, right? So this is oxidation, and oxidation is what? The loss of electrons, remember? Oil rig. So oxidation is the loss of electrons. So yeah, iodide is losing electrons, so it is getting oxidized itself, and therefore it is a reducing agent. So it is a reductant. Reductant is another way of saying reducing agent. So if it is getting oxidized, then there must be an oxidizing agent, right? And that oxidizing agent is ozone. How do we know that it is an oxidizing agent? Because now you can look at it as a loss of oxygen atom. You can look at it as the loss of oxygen atom. So loss of oxygen atom is also like sort of reduction, talking in terms of the loss of oxygen atom. Also, we can talk about the decrease in the oxidation state. Now, I told you that when the element is on its own, it is not in the compound form, the oxidation state is 0. So here in this O3, which is the molecular form of ozone, the oxidation state is 0. And here in water, the oxygen has -2 oxidation state within the water molecule, but this here again is 0. So we cannot justify reduction or oxidation on the basis of oxygen getting converted into oxygen molecules, or ozone getting converted into oxygen, because this is only loss of one oxygen atom. If you look in terms of oxygen atoms, then yes, this will constitute reduction. But if you want to talk about the oxidation state reducing, then you will look at this ozone and then this -2 on the oxygen atom of water. So this is a reduction, right? So this is how we say that ozone has been reduced, and so this is an oxidizing agent. Okay, so because what gets reduced is an oxidizing agent, and what gets oxidized is a reducing agent. Okay. Now again, I'm sharing my screen. Okay. Okay, so what would you see when ozone is bubbled through aqueous acidified potassium iodide? Yes, colorless solution turning into a brown colored solution. Explain in terms of electron transfer why the change from iodide ions to iodine molecules is oxidation. So you will show this, you can show this, you can show this equation, this one, and then you can tell, right, because the iodide ions are losing electrons, that's why. Okay. Okay. Am I sharing my screen? You can share my, you can see my screen, right? Yes. Okay. Okay, then next part, explain using your answer to B part 2 why ozone is the oxidant in this reaction. And then you can show this other equation that I wrote down. Yes, ozone itself is getting reduced and it gains electron, but it would be better if you show it in the form of equation. Okay, 0 here, 2 plus here, and 0 here. So there's 2 plus here. Now, in order to electrically balance this equation, you want 2 plus should be neutralized by 2 minus. So we know this is reduction, which is the gain of electrons, right? You can write this equation and show that this is, the ozone is getting reduced. Okay, question number 3. Sulfurous acid is a reductant, again, reducing agent. What would you see when acidified potassium manganate 7 is added to a solution containing this acid? So in order to answer this question, you should know what acidified potassium manganate is itself. What is it? What is acidified potassium manganate? Yes, Afan, it is an oxidizing agent. Right. Yes, Ajwa. Yes, it is an oxidizing agent. So now if the oxidizing agent will react with a reducing agent, sulfurous acid, what will happen? What will happen and why? Color change from purple to colorless. Yes, from purple to colorless. Yes, good job, but then why? Why? See, it carries 2 marks. So I think they want to ask, they want you to write why, not just purple to colorless. It contains 2 marks. Color change would carry only 1. Gets reduced to what? Afan? Gets reduced to what? Potassium sulfate will form. I'm not sure about that. I'll have to write the equation and then see maybe. All sulfates are soluble except for barium, calcium, and lead. Maybe potassium sulfate is formed. Yes, beta, that is right. But tell me, reduce to what? Okay, I'm sharing my video. You can see my video as well as my screen. Can you see both? Oh, okay, okay, good, good, good. Yes, Hiba, yes, manganese +2. So manganate is this, and can you see that manganate 7? They have mentioned manganate 7. Can I have another marker? Okay, manganate 7, right? So this is -8, and so -2 multiplied by 4 is -8, right? And so this should be +7 to have this whole thing have a charge of minus. Manganate, so this is +7 here into manganese. Can be 3+, remember 3+ is pale pink. It's so pale that it's almost colorless. Manganese 3+ is pale pink. It is so pale that it is almost colorless. So I think it's manganese 3+. Okay, but you can cross check, Hiba. I did not get hold of the answers to these questions, by the way, and I did not have time. Yes, it's +2 or +3. I have no, I please confirm. I think it's +3. I think. But manganese +2 also exists. So I'm a little confused. Okay. Explain why the change titanium 4 chloride to titanium is reduction. So that's easy. Who wants to answer this? Explain why the change titanium 4 chloride to titanium is reduction. It's okay, I need to. According to the book, +2. Is it manganese +2 which has pale pink color? Yeah, maybe. Okay, then it is +2. Okay, I'm getting a little forgetful here. Okay, this is because the oxidation state of titanium decreased from +4 to 0. Okay, Hiba, yes. Will accept 4 electrons and its oxidation number will decrease. Yes, Ajwa, that is a good answer. Titanium +4 ion will accept 4 electrons and its oxidation number will decrease from 4 to 0. Okay, good job. So this is this you guys can do. Question number 5. The following are examples of redox reactions. Bromine water was added to aqueous sodium sulfide. Explain in terms of electron transfer why bromine is the oxidizing agent in this reaction. So if you want to prove that bromine is an oxidizing agent, you show it getting reduced, because an oxidizing agent will get reduced itself. Okay, so yeah, you just show how bromine is getting reduced. Yes, yes. From 0 to minus. So its oxidation state is decreasing from 0 to minus. So it is getting reduced, and that is by gaining electrons. And then again, you will write that equation, right, of reduction. किस तरह से है? किस तरह से है वो? Okay, sorry. This is bromine gaining 2 electrons. Okay, my video is on. Okay. Okay, so this equation, bromine is accepting 2 electrons, bromide, so this is reduction. Okay, move on. Okay, question number 6. The table below shows the elements in the second period of the periodic table and some of the oxidation states in their most common compounds. What does it mean when the only oxidation state of an element is 0? Yes, it is, and it's a stable form. Its outermost shell has the stable and complete outer shell, and so it is stable, right? And it does not react. So its electrons do not participate, right? Its electrons do not participate in any reactions. Explain why some elements have positive oxidation states, but others have negative ones. Okay. Can I have new participants? The same students participate. Can I have new participants, please? Some elements have positive oxidation state indicating that they have lost an electron and others negative because they have gained. So why? Why? Talk about some atoms have a greater affinity for electrons and therefore they tend to gain. They are more electronegative. And that's why the halogens form anions and they have negative oxidation states because they have greater affinity for electrons. Whereas on the other hand, the group 1, group 2 metals, they have less affinity for electrons and therefore it's easier for them to give away, to lose electrons, and therefore they have positive oxidation states, right? So you will talk about the affinity towards electrons. Okay, you will talk about the affinity towards electrons. Okay, then question number 7. Copper 2 oxide can oxidize butane 1-ol to liquid X whose pH is 4. pH 4 meaning it's acidic. Now, name another reagent which can oxidize butane 1-ol. So you need to have an oxidizing agent here, right? So what oxidizing agents do we know of? Yes, Afan, acidified potassium manganate, acidified dichromate, and air, oxygen. Just use direct oxygen or air, okay? Yes, acidified. It would be better if you write acidified. Yes, I like the fact that Ajwa wrote the whole name. Acidified potassium manganate 7. Yes, that's how you write it. Okay, that's how you will write in the exam. The whole name in parentheses, mention the oxidation state in brackets. Then question number 8. Although methane can persist in the atmosphere for up to 15 years, it is eventually removed by oxidation. What are the products of this oxidation? Yes, what are the products of oxidation? Good job, Ajwa. Yes. No, Maruj, not nitrogen. Yes, water and carbon dioxide. Now a little explanation, please. Sit down, sit down. A little explanation, please. How do you get carbon dioxide and water? Methane is CH4, okay? And so it is oxidized in air by oxygen, okay? Okay, look at this. Yes. Carbonate produces carbon dioxide. Where did carbonate come from, Amana? In this question, we're talking about methane. There is no carbonate here. Okay, CH4, yes, Afan is right. Methane's formula is CH4 and it reacts with oxygen to give us carbon dioxide and water. So one way of looking at it is that there are two elements making methane, carbon and hydrogen. So just add oxygen to both of them. So the molecule that we know of, which is composed of carbon and oxygen, is carbon dioxide. And the other molecule that we know of, which contains hydrogen and water, is water. Sorry, hydrogen and oxygen is water. And so it's easy, right? So oxygen is getting added to both hydrogen and carbon. With hydrogen, it's forming water. With carbon, it's forming carbon dioxide, right? And you can even balance it, right? So now we have 2 oxygen atoms here, sorry, 4 oxygen atoms here and 4 oxygen atoms here, right? And 4 hydrogen atoms here and 4 hydrogen atoms here. Okay. Okay. Yes. Okay, let's move on. Then question number 9. Okay, Afan will do question number 9 and 10 for us. Okay, Afan will explain us question number 9 and 10. So you want me to unmute you, Afan? Let's read the question first. Okay, let's read the question first. 9 part A. Iron has 2 oxidation states, +2 and +3. There are 2 possible equations for the redox reactions between iron and bromine. Looking at the 2 reactions, we know in the first one, iron is getting oxidized. The metal iron is getting oxidized from metal state to iron 2+. The other from the metal state to iron 3+, right? Now the question is, indicate on the first equation the change which is oxidation. Give a reason for your choice. And then part 2 is asking which substance in the first equation is the reducing agent. So the substance which will get the substance which is getting oxidized will be the reducing agent. Okay. Part B, describe how you could test the solution to find out which ion, iron 2+ or iron 3+, is present. Okay. Okay, Afan, should I unmute you? Is that okay? Okay. Yes, you're unmuted.
Okay, so for first question, it is asking which change is oxidation. So we have 3 viable definitions for oxidation. It can either be defined as the gain of oxygen in a substance, the loss of electrons by a substance, or the increase in a substance oxidation state.
Okay.
So now we have these 2 equations with us, and we need to tell which change is oxidation.
Right.
So, so now we don't know in these, it doesn't give a clear statement of which one has its oxidation state increased or decreased, and there's no gain or loss of oxygen involved.
Yes.
So we can use the last third definition, gain or loss of electrons.
Okay.
So we should see which one of the 2 substances, iron or bromine, has lost electrons. And,
yes.
and we've learned from ionic bonding that if a substance loses electrons, it gains a positive charge.
Right.
So after the reaction is over, iron gains a positive charge. So we can say that in the first equation, the change iron to iron 2 ions is the oxidation reaction. And the reason, 2 viable reasons can be placed here. It either loses 2 electrons or its oxidation state has increased by 2.
Right. Right.
Now, which statement in the first equation is the reductant or reducing agent? Now, one thing about reducing agent, it reduces other substances and itself gets oxidized. So we find out from our part I that iron is the substance that has been oxidized. So our answer for this will be iron.
Right, because the reducing agent should get oxidized itself. So iron is getting oxidized. So that makes iron the reducing agent, right? Okay. And can you also do part B for us?
Yes. This one, its hint is present in our chemistry books on page 135. To figure out whether iron 2 or iron 3 ions are present in a solution, we can just add an excess of sodium hydroxide to it and wait for it to re-dissolve. If iron 2 is present, then it will give a light green precipitate of iron 2 oxide. And if iron 3 ions are present, then after it re-dissolves, it will give a red-brown precipitate of iron 3 hydroxide.
Yeah, hydroxide, not oxide, okay? Hydroxide, yes, good job. Very good, I'm happy. I'm proud of you, okay. Now, let's also do question number 10. Can you take us through question number 10?
Yes, sir. Yes, ma'am.
Okay.
Now it's saying about the oxidation states of vanadium. It can either be +5, -4, -3, or +2. Now, the particular one, vanadium 3, it can behave either as an reducing agent or oxidizing agent. So now the first equation they have given us, 2V3 plus Zn will result in 2V2 plus Zn2 plus. Now it's indicating we need to ask which indicate on the following reactant which is the oxidant or oxidizing agent. Now for the oxidizing agent, it will always be reduced as well.
Right.
So give me a minute. Let me zoom in so I can make it clearer.
Are you sharing your screen? Because
No, ma'am. I'm just zooming it on my laptop so it is clear to me. Okay,
okay.
got it. So
Okay.
now, oxidant will get reduced. So here we can say that for reducing the decrease in oxidation state. So in here, if we can consider both. Vanadium, its oxidation state has decreased from 3 to 2. So it has
Right.
become reduced. So
Right.
vanadium is the oxidizing agent.
Right. Right. Excellent. And
And
then
then
part
the
2.
final part, vanadium 3 plus iron 3 will result in vanadium 4 and iron 2.
Right.
So now it's asking which equation is oxidation. Again, we can use the same logic, find which of the substances has increased the oxidation state. In this case, it's vanadium as well because its oxidation state has increased from +3 to +4.
Right. So we will, yeah, okay. So our final answer would be that the change of vanadium 3 plus to vanadium 4 plus is oxidation in this equation, right? Hello, Afan?
Yes,
Right.
ma'am.
Yes. Okay. Jazakallahu khairan. Jazakallahu khairan. I loved it. It was fabulous. Perfect. Okay. Now let's. I hope he explained it so well, better than me, that I don't think anybody has any confusion, right? Add ammonia if a green precipitate forms, it means iron 2 plus, and if brown precipitate forms, iron 3 plus. Okay. Okay, yes. Basically, iron 2 salts are green in color and iron 3 salts are brown in color. So you need to add a base that will react with these ions, and then they will form their respective compounds, right? And the compounds are a different color depending upon the oxidation state of iron. So iron 2 plus, green precipitate, and iron 3 plus, red-brown precipitate. Okay, question number 11. Explain why the positive ions are likely to be oxidizing agents. Why are positive ions likely to be oxidizing agents? Oxidation is the loss of electrons, so they are oxidizing, so they are snatching away electrons from others. Oxidizing agents are snatching away electrons from others. No, if you're talking about them losing electrons, they should be reducing agents, remember? Are you understanding? No. because they have positive charge, so they have an affinity for electrons. So they pull electrons. I mean, because of the attraction between opposite charges, they pull electrons, and therefore they cause oxidation. They oxidize others, and that's why they are oxidizing agents. Can you hold this camera? Can they see my video? Yes, yes, that's right, Hiba. I hope I'm glad that you understood my point. See, metals, for example, remember this diagram that I made? Electron getting transferred from one atom to another. And so this is losing electron. So this is getting oxidized. Okay, and this is gaining electron. So this is getting reduced. And so this is the oxidizing agent. Why? Because it is oxidizing this other reactant. And this is the reducing agent because it is reducing the other reactant. Right, so what they're asking is that why are metals good oxidizing agents? Cations. Why are cations good oxidizing agents? Now, if you remember, our oxidizing agents are acidified potassium manganate, right? So potassium manganate has this very important cation, right, which gets reduced to manganese 2+. And then we have dichromate, Cr2O7, potassium dichromate, right? Here, the cation, this is chromium is the cation, which then gets converted into chromium 3+, right? So we're talking about cations. That's why cations are good oxidizing agents, is because of their positive charge. If this is positive charge, if this has a positive charge, it will be easier for it to pull the electron away from the other reactant. And so that will make it a better oxidizing agent, right? So I hope you got that point. Right, okay. Okay. Deduce which ion is the best oxidizing agent. And you know what? I think this question is a part of, it is just a part. It is a part of a longer question, which they did not give here. You have to choose from a list. Deduce which ion is the best oxidizing agent. You have to deduce from a list. Which ions in the list can oxidize lead metal? So we don't have that list. I don't have that list. So this is an incomplete question. So I don't know the answer to this because I need to see that list. Okay, the following reactivity series shows both familiar and unfamiliar elements in order of decreasing reactivity. Each element is represented by a redox equation. Two of the uses of the series are to predict the thermal stability of compounds of the metals and to explain their redox reactions. Define in terms of electron transfer the term oxidation. That is easy. It is the, yes, it is the loss of electrons. Yes, that was easy. Okay. Then explain why the positive ions in the above equations are oxidizing agents. Because again, because of their positive charge, they will have affinity for the electron, right? They will have the affinity for the electrons. And so they will cause others to lose electrons and they will oxidize the other reactants. B, part 1, which metal in the series above can form a negative ion which gives a pink purple solution in water? A negative ion. Which metal in the series above can form a negative ion which gives a pink purple solution in water? Now, pink purple is manganese that I know of, but it doesn't form a negative ion. It forms a negative ion. Maybe it does. You have all sorts of weird. Oh, yes, manganate. Are they talking about manganate? Yes, yes. Oh, yes. Yes, yes. You are right. I thought, you know, I didn't know that they're talking about a polyatomic ion, like it can combine with oxygen to form a manganate ion. I thought, you know, the metal itself alone. Okay. B, part 2, describe what you would observe when zinc, a reducing agent, is added to this pink purple solution. When zinc is, what would you observe when zinc, a reducing agent, is added to this pink purple solution? In order of decreasing activity, decreasing reactivity. That means zinc is less reactive than manganese. Zinc is less reactive than manganese. Okay. Color change from purple to colorless. Are you sure? Did you see this from the marking scheme? Now, in order for zinc, एक minute, let me think about this a little. Describe what you would observe when zinc, a reducing agent, is added to this pink purple solution. So purple solution meaning it's, let me work this out. Yeah, I did not get a chance of, so this is zinc. Okay, zinc metal, and this is manganate, right? And this is pink purple. Now this will be converted or reduced to manganese 2 plus only if zinc is more reactive than manganese. So is that the case? Is zinc more reactive than manganese? No. No, it's not. Zinc will be able to reduce manganate only if it is more reactive. I don't think you will see any change in here. I don't know the answer in the answering scheme, in the marking scheme. Does anybody have? Does anybody, Hiba, do you know the answer to this? The color of solution will change to colorless. I don't think there will be any change if you ask me, but I might be wrong. I will confirm this. Okay, I will confirm this. I think, you know, this has to do with that potential, you know, this is, we have not done this exactly. Okay, we have not done this exactly, but leave this part. Okay, I will look into it and then I will let you know in the group. Describe what you would observe. Okay, question number 13. I think there will be no reaction because zinc seems to be less reactive than manganese, and zinc can reduce only if you know, manganese is less, if manganese is less reactive than zinc. And according to this series, manganese is above zinc. So I think zinc cannot reduce, but I will confirm. Question number 13, the reactions between metals and acids are redox reactions. Which change in the above reaction is oxidation? Zinc to zinc plus 2 plus, or 2 hydrogen plus to hydrogen gas? Give a reason for your choice. So this is easy. Which one is oxidation? This is easy. Yes, yeah, zinc to zinc 2 plus, because the oxidation state has increased and there is loss of electrons. Okay. Part 2, which reactant in the above reaction is the oxidizing agent? Give a reason for your choice. So an oxidizing agent would be the one which is getting reduced itself. So what is getting reduced? Yes, the acid. You won't write hydrogen, you will write hydrogen ion. Okay, you will write hydrogen ion or acid, because acid means hydrogen ion. Not H2, Amna, H plus. Hydrogen ion is oxidizing. Okay. Question number 4. The rate of a photochemical reaction is affected by light. The decomposition of silver bromide is the basis of film photography. This is a redox reaction. Okay. Step 1 is bromide. Now step 1 is clearly oxidation because it is the loss of electron, and step 2 is clearly reduction because it is the gain of electron. So which step is reduction? I've already answered step 2. Explain your answer, because silver plus is gaining an electron. Part 2, which ion is the oxidizing agent? Which ion is the oxidizing agent? Now, oxidizing agent should get reduced itself. So what is getting reduced? Yes, silver plus. Yes, silver ion. Yes, is the oxidizing agent because it is getting reduced itself. Okay, this other question. When chlorine gas is bubbled through an aqueous solution of potassium iodide, a redox reaction takes place. State the color change expected in this reaction. Chlorine gas is yellow-green, right? But the solution is colorless. So solution will turn from colorless to what? Yes, brown. Yes, so start color is no color and then end color is brown, right? Then identify the reducing agent in this reaction. The reducing agent should get oxidized itself. So what is the reducing agent? Yes. What is the reducing agent? Yes, iodide ion, because it is getting oxidized itself. So that makes it a reducing agent, right? The charge on a silver ion is +1. Deduce the charge on the dichromate ion in this. It's heavy. It's raining so heavily at our place. Is it raining at your place? It's thundering. Okay, deduce the charge on the dichromate ion in this. Yes, it's very pleasant outside, but we are stuck inside. Yes. Okay. So let's find out the oxidation state of chromium in this, right? That's what they have asked us. Yeah. Yeah, you guys give me the answer immediately. You don't, but you have to, you know, yeah, I know you cannot show me the working. Okay, so let me work this out, okay? Oxygen is usually -2, okay? And then chromium, we have to find out, X, and silver, they have already mentioned in the question, is +1. So there are 2 of +1. So +1 multiplied by 2 plus this X, 2X, because there are 2 of them, okay? And then this is 14, 7 2s are 14. Overall, I should get 0 because this is overall neutral, right? There is no net charge on it. So +2 plus 2x minus 14 is equal to 0. +2 minus 14 will give me -12 is equal to 0. And x is 12 divided by 2. And so chromium is +6. Chromium is +6. Okay, did you understand? Yes, chromium is +6. Did you understand how I worked it out? Yeah, it's raining so heavily at our place. Okay, let's move on. Write the ionic equation for the formation of silver dichromate in this reaction. State symbols are not required. Write the ionic equation for the formation of silver dichromate in this reaction. What reaction? This is also, you know, a part of a question. This is not the whole question. There is some reaction they talked about, and that reaction is not here. I mean, they have just mentioned the dichromate. I cannot make an ionic equation just like that because I don't know what the dichromate is reacting with. Write the ionic equation for the formation of silver dichromate in this reaction. State symbols are not required. Does anybody know the answer? Yeah, this is incomplete. Yeah, lightning has entered the chat. Yeah, okay. Is there any last part to it? Explain why this is a readout. No. So that's it. Okay, it's 9 o'clock. And yeah, we will do the rest of the questions, inshallah, tomorrow. Okay, you can let me know what you want me to do tomorrow. Tomorrow will be my last class before Eid. Okay, and then inshallah, we will be done. Right. Okay, Allah Hafiz. Okay, Allah Hafiz. Assalamu alaikum. Do let me know what you want me to do. Okay, otherwise I will do specific heat capacity. Okay.
Allah Hafiz, miss.
Allah Hafiz.
Lafis miss.
Allah Hafiz. Allah Hafiz.
Office, ma'am.
Yeah, because of Eid, Shamim and Huzafa. Because of Eid. Because of Ramadan, sorry. Yes.